So here's another interesting question. Here's a tube which is rotated about its left limb with angular velocity omega. The diameter of this tube is very negligible as compared to L. We need to find out the difference in height of the liquid in the two limbs of the tube. Now for finding out this, we go about solving it in this fashion. We assume a cylinder of water over here. This is a cylinder of water, that is a water body. We have chosen this water body. Let us find out the pressure at this point, which will be equal to, let this height be h2, this height equal to h1. So the pressure at this point will be equal to P naught plus rho g into h1. Many of the fluid mechanics question you will be required to solve by assuming elements like these and then applying Newton's law on those elements. We solve this question in the similar fashion. The pressure at this point A, let us call it A, and this point B, PA was equal to P naught plus rho g h1. We can apply this formula because there is no motion or acceleration of the object in the vertical direction. So for the vertical direction we can have the equation directly. We can solve this also. Let us take a tube of water in the vertical direction. The pressure at this point is P naught. Let the pressure at this point at height h below be P dash, and the density of this is a cylinder of water that we have assumed. Let the area of cross section be A. Therefore, the pressure on the lower surface of this cylinder of water is equal to P dash into A. From the upper surface it is minus P naught into A. So the net force is upwards, and this is balanced by the mg of this water body, that can be written as density of the liquid into A into H, this is a volume, density into volume mass into G. Therefore P dash minus P naught is equal to rho G H. Therefore P dash is equal to P naught plus rho G H. We could write this because there was no acceleration of this water body in the vertical direction. Therefore this equation still holds true. Therefore we can directly write the pressure at this point to be P naught plus rho G H1. The pressure at this point to be P naught plus rho G H2. Let us now concentrate on this body of water, cylinder of water rather, which we have taken. PB is equal to P naught plus rho G H2. Now for this body of water, we can write F net external in the horizontal direction is equal to mass into acceleration of center of mass. This formula is always true. Now F net external, the pressure at point B being greater, the net force on this object in the horizontal direction can be written as PB into A minus PA into A. Let A be the area of cross section here. Let this be A dash. Therefore the area of cross section here is A dash. It will be the same A dash over here. Therefore PB into A dash minus PA into A dash is the net force acting on the object in the left direction. This can be written as the mass of this water body, that is mass of this cylinder of water, that is rho into A dash into L. This is the mass into acceleration of center of mass. The center of mass of this cylinder of water lies here at the center. This central point is performing circular motion with angular velocity omega. Therefore the centripetal acceleration of center of mass will be omega square into the radius of the circle, that is equal to L by 2. Therefore we write omega square L by 2 over here. Now we substitute the values of PB minus PA. PB minus PA comes out to be rho G H2 minus H1 into A dash is equal to rho A dash into L into omega square L by 2. H2 minus H1 is equal to H. Therefore, rho GH A dash is equal to rho A dash omega square L square by 2. We cancel rho A dash to get H is equal to omega square L square by 2G. So, final answer for the difference in heights of the water column in the two tubes is equal to omega square L square by 2G. In this question, we learnt an important method, that how to assume elements of water objects and then apply Newton's law on them to solve the question. The final answer is omega square L square upon 2G.